Okay, hello everyone. Welcome to the hot seat, session 2, part 6. We have a very special guest today. Rick Miron is here with us from United States. I'm pretty sure so many of you around the world know this guy. He's a true educator and researcher. And when I will have his CV now, you will get how celebrity-wise he is in the field of perio and implant. So today we're going to have the chance to learn from one of the masters in the field of growth factors and PRF. I'm sure that this webinar will be full of researches of his work, full of data that you can get from the growth factors, and I think it will be really beneficial for your practice. So Rick, as a tradition, I will have your CV now. Rick is currently the lead educator and researcher at Advanced PRF Education and an adjunct visiting faculty in the Department of Periodontology in Bern, Switzerland, where he completed his PhD thesis and studies since 2009. He has currently published over 200 wow, come on, 200 articles in the field of guided bone regeneration, materials, growth factors, and he has recently been awarded many recent international prizes in dentistry and is widely considered as one of the top contributors to implant dentistry, having won the ITI Undershooter Prize, the IADR Young Investigator of the Year in the field of implant dentistry, and also IADR Sugransky Research Award in the field of perio in 2020. He has also 3 best-selling textbooks. One is Next Generation Biomaterials for Bone and Periodontal Regeneration in 2019. The other book on bone regeneration with Mike Picos in 2019. And also the other book in 2017 titled Platelet-Rich Fibrin in Regenerative Dentistry. With that said, Rick, we are ready from head to toe to hear your amazing presentation, and at the end we will have a discussion and question and answer. The platform.
Perfect. Thank you so much for having me, first of all, Omid. It's great to see you and all your energy and all the work that you're doing here, keeping people entertained during this time. So I wanted to do a talk today, and I'll share my screen in a second, but I just kind of, you know, as myself, I'm a biologist and preclinical researcher. So what I wanted to do was just convey some message from things that we've learned, I would say, in the last 1.5 to 2 years on platelet-rich fibrin, things that are from labs and conceived there, but are very, very clinically relevant. That way there, you know, after these 45 minutes, you'll be able to say, you know, hey, look, I've learned these things and they'll be applicable to your practice. So I'm going to go ahead right now and share my screen, and then we'll get started. All right, so again, I titled this talk Understanding Platelet-Rich Fibrin for the simple reason, you know, it's a huge topic, as you can imagine. More and more people are getting involved in this therapy. It's quite easy to do when you've learned a few simple concepts, and relatively cheap, and I think that's the reason why it's widespread across the world. For those that don't know who I am and kind of my background a little bit, I always give credit to the supervisors and people that I've worked with. I'm Canadian, I was born and raised there. And after my master's in implantology, I did a master's project with Straumann implants, etc. And I was awarded a big scholarship, fully funded to do a PhD anywhere in the world. And it paid everything for 5 years. And I decided to go to Bern, Switzerland, simply because Bern at the time was one of the top ranking dental schools, currently ranked #1 when you look at, you know, citations per paper, etc. And a lot of it thanks to these two guys here, of course, very well known in the field. Perio, I don't know anybody better than Tony Scullion. I mean, he's done a lot of work with growth factors, with emdogain, and he's been part of a lot of our preclinical studies on platelet-rich fibrin. And Danny, of course, is very well known in the implant field for all his work with implants as well as with GBR procedures. So I always give them credit for the ongoing work that we do in the labs. When I was brought in to Bern, Switzerland, I was working in the labs. And my job was to work with these big pioneers in implant dentistry and perio and help develop new materials and do all the preclinical research for materials. So when you think about this logically, before you ever get a new implant, always that implant has to be tested in a lab with cells. Then we do animal research with animals, and then we quantify osseointegration, BIC, et cetera. And then it goes to these guys, typically. They do the first human studies, and then when everything's FDA cleared and CE approved, it goes to market. And the cool thing about my job is, I'm always seeing things that are literally 3, 5, 6 years from now, kind of what's going to be available. So I'm kind of living in the future when it comes to this space. And as you can imagine, working with these guys, every single company wants to send their new growth factor, their new biomaterial. Every company wants to collaborate with these guys. And what would these guys do? They'd say, no problem, we'll do some research. They give it to me. They send it to the lab, right? We start playing around with it. And then we're able to characterize the biological activity because of all these different materials: allografts, xenografts, membranes, new membranes, hyaluronic acid, everything that you can think of related to biomaterials and implants was tested in our lab. And so it's kind of a cool space to live. In that space, of course, I work with these two guys. Dieter Bossart's one of the best histologists in the world. Reinhard Gruber at the time was head of preclinical research, so I'm very endeared to the collaborations that I've had with these guys over the years. 3, 4 years ago, I relocated to Florida. So I'm Canadian. I got a license in North America, relocated down in South Florida, had a lab that was named after me, so just the Myron lab. And here what we did was the same thing that I was doing in Bern, Switzerland since 2009. I just said, I'll do the same thing, but I'm going to do it in North America now. So I take the biomaterials from the companies, we test them in the lab, we do the first studies with it, and off they go to market. And was a lot of fun working here. Like I said, I've done a lot of work in the facility. Now, if you can imagine this, I have all this knowledge on biomaterials, and one day I get a phone call from Quintessence, and they say, you got so much knowledge on biomaterials, why not write a book on the topic? And I did it with Yufeng Zhang. And Yufeng here, very similar situation to me, won a scholarship from China, decided to go anywhere in the world. He was located in Bern, Switzerland. So we teamed up there in 2009, 2010, ran a whole bunch of studies. Of course, between the two of us, we knew a lot about biomaterials. I always say to clinicians, the worst place to learn about biomaterials is from sales reps. And unfortunately, that's where, especially in North America, that's where most knowledge comes from. When there's new biomaterials that are coming out, a lot of people hear about this information from actual sales reps. And kind of the issue with that is, they have only a certain amount of actual knowledge on these topics. And when you think about how many great implant dentistry books there are in the world, there's tons of them. There's never been kind of a reference biomaterial book. And that's where this book just said, this is the properties of autogenous bone, of allografts, of xenografts, of all these different materials. And here's how you should use them, okay? And I think it's very valuable. I don't make any money from the book. We donated all the royalties to create a scholarship, so I'm not doing it so I make any money at all. It's not my purpose. The purpose was really to fill this big need in the implant dentistry field, especially to try and make sure that collaborators really understand how to work with these materials. Now, I was very shocked. I got a phone call one day as well afterwards. The book was released, top 8 books in the world. Quintessence publishes this. It was the #1 most sold book in the world earlier in 2019. So I was like, obviously I was very shocked about it because, I didn't think people loved biomaterials as much as I do. But again, it just comments on the fact that, there's really a need for understanding these biomaterials. Before I go into platelet-rich fibrin, a lot of cool studies that we're working on. I wanted to show just kind of the work that we do in this preclinical lab. So I was going to show a few slides on this new osteoconductive bone adhesive, just to give people a feeling of kind of the work that we do. Companies based out of Boston did some work with Dr. Picos here and Dr. Fugazato and a couple of other colleagues. David Cochran, I'm very close with as well, did some work on Emdogame with them. Sure enough, there was this new company that came out and they made basically a bone glue that was totally biocompatible, okay? And so what it is in a nutshell is a group of researchers, like many of us, we're trying to figure out why is it that certain type of underwater creatures can literally stick on bridges, let's say, right? Why is it that some sandcastle worms can literally stick on a bridge underwater and they can stick to the metal for hours at a time? And how do they do that, right? And so a group of researchers, again at MIT and Harvard, figured out the exact proteins that are responsible for that glue-like properties. It's totally biological. And then they mix it with bone graft, totally synthetic, totally biological, no polymers in here, nothing at all, okay? And it gets hard over time. And this is an amazing video just to show you the properties of it, because when you look at this, you can actually take this material This is a femur that's been cut in half here. And within a few seconds, it already starts sticking. Okay, within 10 minutes, look at the strength of the material. Okay, it's unbelievable, completely unbelievable. And like I said, this is something that when you think of implant dentistry and you think of wanting to have primary stability of your implants, you think, wow, you know, talk about a cool material, right? So we had done all the studies on this, and I'm not going to kind of go over what we've done exactly in the lab in animal models, but long story short, this is being used in clinics today. Okay, and this gentleman right here is Dr. Michael Picos, who's located very close to me in Trinity, Florida. First guy in the world to ever use this material. So again, it's insanely cool. It's totally biological. And when you think on the applications, right, you can take this material, it's fully resorbable. I'm not showing the data, it's in the textbook, of course, but fully resorbable and replaces with native bone and never have to worry about implant stability anymore. Okay, unbelievable. So very, very cool work that we're doing. And Dr. Picos, like I said, since October, early October was the first time that he placed the first case. And he's been doing it now for several months, has a lot of cases. In fact, we're in the process of writing a case series. And when this is done, then there'll be a few more studies and away it goes to the rest of the clinicians. So this is one, like I said, that I think is extremely interesting. And I think anybody that gets the chance to use this first, and such as yourself, Omid, maybe you can, you know, get your hands on some of this stuff, run some education programs with it, because I think it's going to be a game changer in implant dentistry. A lot of credit to Dr. Picos here and the work that he's done. Like I said, if you want to read a really great textbook on augmentation, bone augmentation, sinus grafting, highly recommended for all the work that he's done. Okay, so platelet-rich fibrin, another interesting biomaterial, there's no question. And done a lot of research on this since about 2012. And the group and I have done an insane amount of work on this topic. Luckily, we've been funded by different private sources, literally university funding, etc. You know, the biggest problem that I always say with platelet-rich fibrin is the following. When you have a centrifuge, all you're buying are tubes and butterfly needles, okay? And so what happens, and I've collaborated with a lot of even big companies trying to get research funding to do better work on this field. And the problem is, and the companies will say this, they say, Dr. Myron, when we sell one implant, you know, that's $200 for one. And with that, you get a bone graft that's $100, $150 and a membrane. And so there's all kinds of money in those fields, right? For one case, they might make a few $100s. And then if they sell enough of their biomaterials, of course, there's lots of funding that can go around for us to improve the field further, which is great. Think of platelet-rich fibrin. You're a clinician, you might buy 100 tubes, maybe once every what, 3 months, 6 months, some people every year. And the problem is the companies are only making, you know, if they buy a package, 100 tubes for $100, they might make maybe $30 only. And as a result, nobody's investing any money into this field. When I talk about platelet-rich fibrin, I always say, to this day, it is the most utilized biomaterial in all of dentistry. That's probably the least well studied. A lot of papers that are not very well conducted, a lot of trying to figure out what's going on in the field. And of course, when we started working with this in Bern, Switzerland, and with the reputation that we have with our clinicians, you know, we wanted to try as much as possible to advance the field. And it's one of the reasons why this first textbook was written on this topic. Now, when we talk about PRF just as a whole, always remember it's blood cells, right? And you're using a centrifuge basically to separate cells based on density. Light things go to the top, heavy things go to the bottom. You can see from this simple picture here, these little platelets are the light guys. White blood cells are the medium guys, and red blood cells are typically the heavy guys. And one thing that's overlapping is the size and shape of red blood cells and white blood cells is very, very similar, actually. And so it's very hard to actually get proper separation of white blood cells, much easier to get the platelets concentrated. And I'll show kind of the data that kind of highlights this in a little bit. PRF, like I said, I'm sure most people listening are using it, so I don't need to go into the biological properties. You know, everybody knows that it makes a fibrin clot. There's different growth factors in there, and there's different cell types. We're collecting platelets, light guys, leukocytes, and a lot of PDGF, of course. It's the growth factor that's literally derived from platelets, VEGF. Not so much BMP2, although it's found in extremely low doses. I like to not even mention it too much because it's not really a big bone enhancer. Of course, we've learned with things like platelet-rich fibrin, it's very good for soft tissue wound healing, okay? The three main growth factors, what they do, and we express this to patients as well. I just say, look, this is a therapy that's going to do the following three things. It's going to improve blood flow, okay? It's going to help recruit stem cells, and it's going to help these stem cells multiply, or the cells in the area multiply. And that's the reason why we can use it everywhere. You know, sometimes I hear speakers and they say, well, PRF is osteoinductive. And I say, well, do you know what osteoinductive means? And they say, of course I do. I say, what does it mean? It means that it can make ectopic bone. I say, great. I say, so you think PRF is going to help make ectopic bone? And then I say, well, how do you use it in so many different fields of medicine then? How can you inject it in somebody's face and it's going to help fill collagen and other things in a face? Or how can I put it in somebody's knee and it's going to help make cartilage in that person's knee? And the answer is, you know, these following three properties, very, very important to understand. One, helps blood flow. Two, helps recruit cells. And three, helps proliferate cells. And that's why it's so important to understand these three things, because, you know, I can give the perfect case. A lot of people will use PRF alone in extraction sockets. I say, fine, okay? I don't think it works as well as a bone graft naturally, but biologically, if you take PRF and you compress it, you put it in an extraction socket, as long as I have all my bone walls, okay, how does it work? Help the cells vascularize. So this area is going to be more vascularized. That's great. It's going to help recruit cells. We'll have bone walls everywhere here, going to recruit stem cells into that space. And then it's going to help those cells proliferate. So what cells do I have there? I got bone cells. They're going to proliferate, and it's going to help make more bone. Okay, great. Okay, biologically makes a lot of sense. What happens if I'm missing my buccal bone now? Okay, well, biologically, how does it work? Well, it's going to help. I put it in there. It's going to help make blood flow. Great. Now it's going to recruit cells. Well, now I got my bone walls here, but I got no bone cells here. I got soft tissue cells. So then the soft tissue cells are also going to be invaded into the space. They're getting recruited. And then these cells are going to proliferate because you got the growth factors that help with proliferation. What proliferates faster, soft tissue or bone? Soft tissue. I got a problem, okay? And that's where, when you understand these things, then you can kind of make sense of, you know, where you can use PRF, where's it going to be effective. You know, I see a lot of people using it for, you know, gingival recessions with no keratinized tissue. And then all of a sudden it makes keratinized tissue. It's, you know, these things or these concepts, they don't make any sense at all. Why do you go get a connective tissue graft in the first place? You go to the palate to get keratinocytes, right? And so if you have an area with no keratinocytes and you take platelet-rich fibrin and you put it there, you don't have any keratinocytes in platelet-rich fibrin. So you have a problem. Your problem is your defect site is missing keratinized tissue. You got to go to the palate and get a connective tissue graft. That being said, if I do have a nice band of keratinized tissue, and the rule of thumb here is, you know, 2 millimeters or more, then of course you can take platelet-rich fibrin. What will it do? It'll help revascularize the area, help the cells get recruited, and help those cells proliferate. So if I already have keratinocytes in the area, makes sense. Okay, so, you know, just to kind of go over, you know, the biology there of how this works. Okay, so again, we're going to use a centrifuge now to collect these cells and separate layers. A lot of work been done between the different, you know, pioneers of these different fields. Of course, Joseph Chacroun's big concept was, you know, remove the anticoagulants. Even to this day, like I said, a lot of debate between these different colleagues. You hear people that's still lecturing on platelet-rich plasma, and they say, well, it's the same thing as PRF. You know, we've been doing this way before that, and we didn't use anticoagulants all the time. You know, there's a lot of mix up there in the field. You know, don't really get involved in that kind of stuff there, but biologically understand that clotting is very important for healing, okay? And that was a message that Dr. Chacroun has really been promoting for years and years. And it's very straightforward. If you think about it, if you cut your arm and you start bleeding out like crazy, the first thing that's going to happen is you're going to get a clot that forms, cells will get trapped in the clot, growth factors get trapped in the clot, and then healing is going to occur. So if you prevent that clotting, that first step, of course, it's going to delay healing. And that was the major problem with PRP or PRGF over the years. And one of the reasons why they were not used very frequently to this day. So again, we're going to draw blood. Now, the disadvantage is you got to go fast. Everybody knows that, right? It means that when you draw the blood, it's prone to start clotting. And you got to get this in a centrifuge rather rapidly. Now, tubes. You know, what we learned recently is that the tubes are a lot more important than people think. And in my quite honest opinion, the tubes are a lot more expensive than centrifuges. And amazingly, you buy these tubes for only a few cents to a few $1.35 probably are the most expensive ones, or $1.55. And they are critical to the success of platelet-rich fibrin. And we've learned that more recently. long story short, platelets, like on implants, if I have a dental implant, all these dental implants were coming out more recently, and we've done a lot of work in the lab. The more hydrophilic they were, the more water loving they were, the more they would integrate a little bit faster. So, Straumann was one of the first, and they have a lot of surface technology. We're going to make SLA active, right? And what is SLA active? It's simply a hydrophilic implant surface. More water loving, platelets bind a little bit faster. They release their growth factors a little bit faster, clots form faster, and then healing occurs a little bit faster. And you see the implant videos where they take an implant, you see them dip it in a little bit of blood, and either you see the blood start rushing up the threads, etc. That's a hydrophilic surface. So platelets, the same thing in a tube. If the tube is very hydrophilic, and that's typically a glass material, or you can have silica coated plastic, or even some people have created titanium PRF tubes, which I'm sure you've seen as well. Very interesting, but the concept is, if it's more hydrophilic, platelet likes it more, platelet binds to it faster, clot forms better. And the opposite is true on the other side. So on the other side, if you want to use liquid platelet-rich fibrin for facial aesthetics, for knee injections, etc., you need to make a very hydrophobic tube. Then that cell on that wall, he wants to go bind there. He can't bind because it's very hydrophobic, water repelling. He's pushing the cells away. They stay liquid longer, okay? And they just float around in the liquid, okay? And that's the reason why it stays liquid longer. Long story short, if you're one of these clinicians that have problems with clotting, sometimes, clot's not forming after you spin, that's simply an issue with your tube. You got to get a better tube, a more hydrophilic tube. And on the other end of the spectrum, if you're one of these clinicians that are using tubes and you're saying, hey, 5 minutes after I spun, it's already started clotting and now I can't do my facial injections or knee injections, all you need is a more hydrophobic tube. Okay. And our lab spent much time developing these two types of tubes. And I'll show you some of the work and research we've done in that field, which I think is very, very interesting. I'm going to skip over this stuff here. Like I said, everybody knows how to make sticky bone. I'm sure you guys are all familiar with it. And kind of the concept, like I said, you're just taking these PRF membranes, mixing them inside, of course, and then you get this nice little workable and bone graft. And the sticky bone is, of course, much easier to work with when it comes to handling and doing sinus grafting procedures, etc. Okay, like I said, that's not something that I want to spend time on because, of course, many of you guys already know this. What I want to talk about, though, is the research now that we've done more recently. This is a great study that we did. Title: The Effect of Age, Gender, and Time Between Blood Draw and the Start of Centrifugation. Why did we do this study? We did this study because a lot of clinicians were complaining. They're like, Dr. Myron, sometimes my membranes are this big. There's a lot of variability going on, okay? And I'm sure if you've done enough PRF, you've had this experience before. And so let me explain exactly why that happens. And more importantly, when we did this study, we wanted to say, how long do you as a clinician have between when you first do that blood draw, okay, to when you actually have to get it in that centrifuge machine? Because that's not a question that a lot of clinicians know, right? I can go around, ask an empty room, do you have 30 seconds? Do you have a minute? Do you have 2 minutes, 3 minutes? People don't really know. And so what we did is we did this research project with one of my students here, Anika Dan. We had 6 machines set up in the back of a room, all the same centrifuge, did a blood draw on somebody. So let's say you take my blood, tube number 1 goes in machine number 1, we start it right away, 0 seconds. Machine number 2, we start after 30 seconds. Machine number 3, after 60 seconds, 90 seconds, a minute 20. And then after the spin, we can then compare and see what happens from that same person's blood draw done all at the same time, what happens to the sizes, okay? So here's the effect of time on PRF membrane size. And what we found was that by 90 seconds, it was already significantly smaller, so 13% smaller. Where it was really bad, though, was 120 seconds, 23% smaller. And when we looked histologically, 50% less cells, okay? Why is this a problem with platelet-rich fibrin? Just think of it logically. This is my tube of blood. If I let this sit here for 2 minutes, that's 2 minutes of time that fibrinogen and thrombin are slowly going to convert into fibrin. So it's starting to form that fibrin clot before I even started trying to separate the layers, right? I'm putting it in the machine to separate the layers, but now I'm getting a little bit of a clot. Then I start spinning. Those cells are trying to pass layers, but they can't pass as effectively because, of course, it's already started clotting, okay? So we always tell clinicians about 90 seconds is what you have, okay? 90 seconds. How long does it take to draw a tube of blood? About 15 seconds, okay? And so when you understand this stuff, actually, the fastest you can get, the most tubes you can get into a machine at one time is about 6. By the time you draw 6, By the time you go 7, you've already passed your 90 seconds, I can promise you. Okay, so very, very important concept here. Another thing that's kind of interesting as well, if you're going to make sticky bone, you're going to be drawing white tubes and red tubes typically at the same time. And a lot of people will put them in the machine at the same time, same protocols, whatever. No problem. Okay. Preference, of course, is to use 2 machines, but I understand that most people only have 1. Which tubes do you put in the machine first, or which tubes do you draw first? The white ones or the orange ones? Okay, the plastic ones or the red ones? Okay, and the answer is the plastic ones. Okay, whether it be the white tubes or the orange tubes, always, or the green tubes, whatever people are using. I don't really care about the colors. Always the hydrophobic tube. Okay, why? Think about this logically. If I draw that first tube, it's going to be sitting there for, let's say I draw 6 tubes. It's going to be sitting there for 90 seconds. Which tube do I want sitting there for 90 seconds? The one that's not going to promote clotting, which is the plastic one, because it's hydrophobic, so it's not going to clot, or the other one that's going to promote clotting. And of course, when you understand that, and I put it this way, it's very obvious, right? The plastic one. Because the plastic one is not going to clot, which means that it's going to stay liquid longer. So if it's been sitting there for 90 seconds and then it goes into the machine, I can still separate my layers effectively, okay? So another important trick, like I said, I'm just going to give a couple little small pearls that way that you can go back to your clinics and kind of learn from these. Another interesting one, who makes bigger membranes, males or females? And the answer is females. So we know this. Why is that? Well, it has to do with the density, essentially, the hematocrit counts of the blood, right? Who has more red blood cells, men or females? And the answer is men, right? They have more hematocrit counts. So when you look at the numbers, about 40 to 54%, women is 36 to 48%, which means that if I have a tube of blood and I want to separate layers, always remember that in a man, it's thicker, so it's harder to get the separation. And as a result, if I use the same protocol, the men is going to have a smaller membrane. Who's going to have a smaller membrane, or how much more? About 17%. So I always say 20% just to make life easy. Okay. Females typically will have 20% bigger membranes. And it's the exact same thing with older patients. Okay. The older you go, of course, the less red blood cells you're going to have. As a result, the bigger membrane you're going to have. So another little pearl here for your practice. When you have a patient, an old female patient, that membrane is, I promise you, always going to be bigger. If you have a very young patient, and especially if this patient is an athlete, okay, if they're athletic, they typically have more red blood cells, or if they live at high altitude, same thing. A young man, example, 18-year-old man or 16-year-old man coming in for third molar extractions, and I'm going to draw pure F, I expect those membranes are going to be 25, 30% smaller, just based on the data. And that's when I can logically say, well, you know what, in that case there, I'm going to spin a little bit faster. And we do, okay? You can spin, let's say, instead of 200G, maybe go up to 300G, or you can increase, an extra 2-minute spin protocol just to get a little bit more separation, okay? You don't need to do it, right? It's not necessary, but I'm just explaining why this occurs and why there's variability in that field. Now, I got this slide here from Dr. Tuttle. I liked it a lot because it kind of explained in a nice picture, kind of the evolution of platelet-rich fibrin. And I'll talk more about, what's been done over the years and kind of where we're at today and kind of where we're still going. And this is a field that I think still has a lot of room for improvement. And I think every year we're learning more and more about the concepts. And I think, in breakthroughs, there was obviously the LPRF protocol, which was a big thing, of course, back in 2001 and onwards. And a lot of work was done by Ganazzi in his lab in Germany that talked a lot about what's considered now the low speed concept, which very interesting and accurate work. Like I said, we've verified and confirmed it and done a lot of work with this concept about 5-6 years ago. Very simply put, when you spin fast, what happens? If this is your tube or your spinning, the faster you spin, the more the cells go down. The longer you spin, the more the cells go down. So if I keep spinning and I keep spinning and I keep spinning fast, the more the cells go down here. But the problem with PRF is that you take it from the top of the tube. And so this German colleague found that we were spinning too fast. And if you think about it logically, and even when you discuss with some of the pioneers and the people that work with platelet-rich fibrin for 15, 20 years, back then they had no idea about spin protocols. All they were trying to do is say, I have to make sure that I spin fast enough that I separate my layers before the clot actually forms, right? It's a logical thing to do. I'm the first person to ever remove anticoagulants. We spin fast, we get the layers separated, and then, you know, we have platelet-rich fibrin, which is great. But when you actually looked at that histologically from top to bottom, you started to realize, hey, there's a lot of cells that are in the red portion that we've lost, okay? And I think that was a very, very big breakthrough. Of course, my group, between those years, we were very active in the platelet-rich fibrin field as well. A lot of credit goes to Dr. Kobayashi here, who did a lot of these basic studies with me. But very simply put, this is TGF-beta. This is from 15 minutes to 10 days. This is the same person's blood. Everything's identical. L pure F. When you go a little bit slower, okay, A pure F. So we go a little bit slower, we get more cells in the upper layer. We get more growth factors that are released. And if you go less speed and less time, you get even more, okay? And it was a way to further optimize platelet-rich fibrin, which was cool because then it meant, you know, from the same machine, as long as you could change the settings on your device, you could get literally up to 4 times more growth factors only by changing the actual setting on the centrifuge, which was, you know, fantastic. And did a lot of work in this field. Now, few things that you got to understand when you understand this, and this is from the textbook. When you go fast for long periods of time, always remember that you get a big layer separation, right? You will get a bigger membrane if you go faster. It's obvious. But the problem is when you look at the amount of cells at the higher speeds, much lower than when you go at the lower speeds, right? And of course, if you got more cells, you're gonna have more growth factors. So again, very fast, high time. This is lower speed. This is lower speed and lower time, okay? Now you get more than 4 times more cells and growth factors, but your membrane about half the size here, okay? So it's very easy. If you're gonna mix this with a bone graft or put in an extraction site, whatever you're gonna do with it, you're much better off spending, you know, double the amount on tubes and have 2 of these guys as opposed to have one of these guys, right? Logically, it just made sense because each one of these has 4 times more cells and growth factors than this guy right here, okay? And like I said, that really revolutionized the field back then. Great concepts that were pioneered. Now, in the field, of course, a lot of different companies, a lot of people always debating, and you know, there's a lot of nonsense going on in this field, especially. And our group in Bern and our group in China, of course, we were not really focused so much on what machine you're using or different devices. It was more, you know, understanding the concepts. So back in 2017-18, we got 2 machines of each company. This is Salvin's machine here, you can see. This is the Duo from Process, and this is the Intraspin device. And I just said, you know what, if that concept is true, the low speed concept, it is applicable to every single one of these machines. There's no reason why one person, because he's using this machine, should have to switch and buy this one or vice versa. These are just devices that spin around in a circle. And so we started doing work on this topic in the lab. And this is Yufeng right here. This is our book, obviously. This is actually in China. You know, what's crazy is the coronavirus started in Wuhan, where he's located, you know, and I've been there many, many times. So, you know, they have had a huge problem with that, but they're finally getting reopened up now. So now we collaborated with engineers. Understanding centrifuges is not so complicated, actually. I mean, I wouldn't expect everybody to be able to do all these calculations, but the gist of it is, you know, as long as you understand what you're doing, you can take any one of these devices and calculate to get relatively the same G-force. Every machine is a different size, okay? All have different angles, and it's calculated between the RCF max versus the RCF min, okay? And the difference is here. Always remember that the RPM is one place that people get mixed up, okay, with RPM. If I'm spinning at, let's say, 1,000 RPM and my radius is this big, okay, and I'm going around in a circle like this, that's 1,000 RPM. I get a certain G-force. Imagine if I still spin at 1,000 RPM, but now my machine is this big, and now I'm doing this 1,000 times a big one. Of course, the G-force here is way, way, way bigger than it would be if I'm spinning at 1,000 here. The biggest problem that you see in the literature is that people always say, oh, you're spinning at 1,300 RPM. Okay, I'm going to do that on my machine. And they don't take into account that the machines are different sizes. And that's where the big mix-up is, okay? And that's one of the reasons why we did this study, to try and optimize this. When we did this study, of course, we optimized all the devices, but more importantly, the one thing that we learned that was so interesting was how important the tubes were. And that's where we started on tube research. we were comparing the different machines at the same G-forces, etc. And sure enough, sometimes one machine was always coming out with bigger membranes, better membranes. And we were like, this makes no sense. Mathematically, we calculated everything. It makes absolutely no sense. And sure enough, had everything to do with just the tubes. And that's when we learned that the tubes matter a huge amount, okay? And so the way that we then looked at this, we said, okay, we got 3 companies here and we got 3 different types of tubes. What I'm gonna do is, I'm gonna take one person's blood. So let's say my blood. I'm gonna take 2 intraspin tubes to balance the centrifuge. I'm gonna take 2 PRF tubes from process and 2 tubes from Salvin, draw all 6 at the same time, all in a random order, and then I'm gonna put it in one machine. And then we're gonna spin and see what happens. Which means that I'm using the same person's blood, I'm using the same protocol, everything's the same, the only difference is the tube, okay? Then you can really evaluate how important these tubes are, okay? So we were drawing 6 tubes and putting it in one machine, 6 tubes, another machine, 6 tubes, another machine, 18 tubes from the same person. Can you take 18 tubes of blood from one individual? The answer is of course, right? It's 180 mLs of blood. Always remember that when you go to a blood lab, every single week, you can give up to 300 mLs, no problem, weekly. Okay, so it's not a big deal to take out 180 mLs and do these types of studies. And this video, when we were doing this was live actually. I made all these videos because, you know, at the time I was like, man, this is so crazy because nobody knew this at the time. But have a look here. This is the intralock machine, and these are the tubes. So S is Salvin tube, C is Chacrun tube, I is intraspin tube. Here's the Chacrun machine. Again, the letters, here's the Salvin. And when you look at it, look at the size of the intraspin tube here, how small this is versus this guy or this guy. These are the glass tubes versus the plastic ones here that are silica coated. Intraspin, look at how small this guy is compared to these guys. And same thing here, okay? And we learned actually from the study that when we looked at the machines here, intraspin machine, process machine, Salvin machine, and then the tubes, intraspin tube, look at black intraspin tube. No matter which machine we spun on, that intraspin tube was always the smallest. And the process for PRF tube, always the biggest in this case here, okay? Very interesting. And this is the same data, just displayed differently. Intraspin tube in the different machines, always smaller, okay? Process for PRF tubes, always bigger. And amazingly, the best result was obtained when we used the intraspin machine with the process for PRF tube, okay? So again, it shows that, you know, the companies have not really optimized, let's say, everything perfectly. But anyways, look at the difference between the machines here. Only 10–15% difference between the machines. Look at the difference between the tubes. 200 to 300% difference between the tubes, okay? And that's the reason why I always tell people, I say, I don't really care which machine you're using, but the tubes matter a whole lot more than do the tubes, okay? Very, very important concept there. Now, this paper here, one of them that we won a huge award for, and I think it's probably the best paper ever published on platelet-rich fibrin so far, titled A Novel Method for Evaluating, Contemplating, and Quantifying Platelet-Rich Fibrin, and some of the work that we did leading up to horizontal centrifugation. The problem that we have in the field of platelet concentrates, you know, the techniques are not very good actually to quantify a platelet-rich fibrin. So what we do typically is you have plasma, you take out the plasma and you send the plasma to a blood lab and you say, how many, you know, you just set it to a regular complete blood count. How many platelets do I have? How many leukocytes, etc. Okay. So when I look at this method, the issue with it is that Ganapti did so much great work showing histologically that all the cells were at the bottom when you went too fast and you got a better even distribution if you evened it out on and on and on. The major issue here when you use this method is you can't tell where these cells are located. When it goes in a liquid solution like this, it gets all mixed up, you send it to a CBC, and everything looks relatively similar. And so again, this is a nice example here that we have in one of our papers. At the LPRF protocol, bunching up all the cells right at the buffy coat layer or below it, and nothing in these upper layers, which means that if I have a fibrin clot that's formed there, I got all my cells here, and imagine I go lay this as a membrane, for example, and I got all this regenerative power down here and nothing in the upper portion. And that was one of the reasons why, you know, with this method, when you look at the very end here, not a whole lot of difference between the two, depending on how you quantify this. So I said in our lab, I said, you know what, guys, we're going to change this up. Instead of sending the entire plasma layer out there, we're going to take PRF and we're going to divide it into 10 different layers, equal, 1 cc each. Every single one of these Cs we're going to send to a blood lab. every single layer. And that way there, I will be able to tell you exactly how many cells after the spin protocol, whatever the companies are recommending, what is in layer 1, what is in layer 2, what is in layer 3, all the way down to the bottom. And I'll be able to figure out this way precisely where all these cells are going. And the way we do this, of course, we just use a pipette, okay, from the top, 1 cc down at a time. Now, always remember, if you do this method, you're always going to have one layer here, buffy coat zone, okay? A little bit of yellow and a little bit of red. You're going to have that zone, and that's the zone that I'm paying particular attention to, because you're going to realize there's a lot of cells in that area, okay, all the way down. So here we go, intraspin machine, intraspin protocol. When we do this and we spin, again, this method is really cool because obviously it's very, very accurate. You can even take the buffy coat zone, that 5th layer here, and you can see the separation where it's occurring. And later on, we can even just quantify the red and just quantify the yellow here. And I'll show you how we did that. Okay, 1, 2, 3, 4, top layers. 5, that's the mixture, the buffy coat zone. 6, 7, 8, all the way down to 10. Okay, here's the data. Number of leukocytes, number of platelets, number of lymphocytes, number of red blood cells, neutrophils, and monocytes, okay? The way we look at these graphs, this control is the average in that person. This is the first layer, the very top, 1, 2, 3, 4. Where the arrows are here, that's the buffy coat zone, 6, 7, 8, 9, 10. So again, here, red cells, you can see they're starting in layer 5, which makes sense. That's where the buffy coat zone starts, and all the way down. Look at the platelets. Amazing. All the platelets are located in layer 5. Okay, right at the buffy coat, which means that this membrane using that protocol has nothing in these upper layers, all the cells right there. Look at the leukocytes. Nothing, 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 nothing. Layer 5, look at even worse than this is there's more actual leukocytes in the red layer than there are in the actual platelet-rich fibrin. And you know, I made the comment, and I know Ganazzi did as well in one of his papers regarding some of the work with this company, but amazingly, you actually have a decrease of leukocytes when you spin at this protocol. And you know, it's called leukocyte and platelet-rich fibrin, leukocyte-rich, platelet-rich, but it's actually not leukocyte-rich. The protocol is a little bit too fast. And it was one thing that Ganazzi reported in 2014. This is just a really good method to really show clearly. It's like saying, hey guys, take a look at the data this way here. You know, look at where the cells are. You know, you're spinning too fast. Now, of course, the work that was done more recently with the APRF protocols make a lot of sense. Take a look at this now, right? Now I have a nice even distribution of platelets throughout these upper layers. And that was the reason why these protocols really did well, because of the nice even separation. Now look at the leukocytes. Still not accumulated in those upper layers. And that was a little bit surprising when we saw this, okay? Still in these bottom layers. And I know why this occurs now. At the time when we were doing this, you know, we're figuring things out. Has to do with the fixed angle centrifuge, which I'll explain in a little bit why this happens. Now, when you look at these two here, of course, these are fixed angle machines, which means they're 45-degree angles, or, you know, between 30 and 45. If you have one of these machines, I don't care which one you have, spin out a protocol that's more similar to the APRF protocol, where it's closer to 200 G on a fixed angle centrifuge, you will get a better even distribution of these cells, okay? No question. And this is just a little diagram from our paper. You know, what do you want to do? You do it this way, all the cells are there. You do it this way here, you get a nice even distribution of those platelets. The next question that we asked in the LPRF work, when we looked at this and we said, take a look at the data here, there's more leukocytes now in this red portion here, and all the cells are in this buffy coat zone. But this buffy coat has some red cells and some like red portion and a yellow portion. So the next question we ask is, if we take that and we split it, where are the cells located? Okay, so you look here, the red blood cells, of course, this is the average here in the control. This is the yellow layer and the red layer. They're all found in the red layer. Look at the platelets though, okay? A lot of platelets, more platelets in the plasma component, but still a lot in the red. Look at the leukocytes. There's actually more leukocytes found in that red zone than actually in the yellow zone. It was very surprising. And that kind of makes sense, because if you look at this, there's obviously more white blood cells in the red portion than in the plasma portion. And so it makes sense that where these cells are going to be located is primarily, you know, in that zone. Why am I telling you this? When you drop, let's say, your IPRF protocols, that zone closest to that border is the most highly rich area. And in fact, many of those cells are floating a little bit into that red zone. And we've quantified it since then. It's about 0.2 to 0.3 milliliters into that zone, okay? when we actually drop liquid platelet-rich fibrin, far too often, and this is another clinical pearl, where that separation occurs right here, I see somebody going in with the needle and they draw up the top half of the liquid platelet-rich fibrin and leave all this zone here completely, blank. They don't collect it. Big, big, big mistake. Big mistake, because the majority of the cells are floating right there or even in the red. And so if you're doing that, and even if you take a couple of these red blood cells, not such a big deal, because that's where the majority of your platelets are located, okay? Very important clinical pearl there. And really nice article on this topic, Influence of Fractionation Methods on Physical and Biological Properties of Injectable Platelet-Rich Fibrin here. In this study, not my group, done completely by somebody else, people I don't know. Really good paper though. They looked at two fractions were harvested, the IPRF. The yellow IPRF fraction was harvested only the upper yellow layer, while the red IPRF fraction was collected both the yellow and the red zone of the buffy coat. And sure enough, what they found at day 7 and 14, PDGF concentrations were significantly higher in red IPRF compared to yellow group. And they also recommend take a little bit of the red, okay? That makes perfect sense, okay? So again, a lot of cells are floating there. Now, injectable platelet-rich fibrin, a lot of comments on this. I remember reading this paper that came out last year, 2019, injectable platelet-rich fibrin, cell content, morphological, and protein characterization. Very, very good study, and really opened my eyes a lot, because we had some issues with IPRF. I'm going to give you some recommendations for this as well, and kind of explain to you what it is we found. In the paper, one of the comments that this group had made is they said, look at the IPRF, the number of leukocyte gain you get, and the number of platelet gain compared to whole blood. And they were making the argument that it's only marginally better than whole blood. I've repeated this study in my lab. I found two things about it. One, it's more like 200-300% increase, so it's better than it shows here. And so I anticipate actually that when they were taking the IPRF, what were they doing wrong? You guys should all know this by now. They're probably just taking here and not going right up to that buffy coat zone. So again, always, like I said, go take that whole layer, because there's a lot of cells that are there. But more importantly, I realized with my method, my new method, that there was not actually a huge accumulation of cells in that upper layer, and I'll show you later. I published this work with a lot of great authors back in 2016. This is one of my most cited papers on platelet-rich fibrin. Actually, I think it's the first paper where we really characterized injectable platelet-rich fibrin many years ago. Did this work with Masako, with Yufeng, with Sharam Ganatsi, and Joseph Shakrun. In the study, okay, you can download this article. We found that migration was improved in IPRF compared to PRP, which made sense. We also found sometimes that PRP was working a little bit better than IPRF. So in this case here, proliferation of these cells was actually better in the PRP group when compared to IPRF. And we say, logically, that doesn't make any sense, okay? Why should it be that you get better, okay, growth factor release, et cetera, in this IPRF, in the PRP group compared to IPRF? Okay, growth factor release. Take a look at the data here. Collagen 2, always better in the IPRF group. Okay, so we see this here. Problem, let me show you the following figures. Look at this data, VEGF. At the time, could never figure this out. I had no idea why this happened. I remember publishing it and speaking with Ganatsi, with Shakrun about this, and none of us could figure out why is it that the growth factor release on some of these growth factors was actually better in PRP than IPRF. No idea why. Today, I understand why, okay? And I'll show you how you can improve this. When we do the IPRF protocol and we use my method, okay, the IPRF method here, again, number of leukocytes, number of platelets, lymphocytes, exactly the same method that we previously used. Look at the gain of leukocytes and the gain of platelets. What do we find by doing this method? Look at how many platelets you actually left below here and how many leukocytes you left below, okay? What does that tell you? That tells you that you're spinning so slow for such a small amount of time that you're not giving the chance for these cells to actually go to the upper layer, okay? I would say it's probably been about 2 years. We just completely stopped recommending these IPRF protocols. Okay, we don't use them anymore because of this data. There's been 3 papers now that have come out that have shown that the concentration of platelets are quite low in these formulations. Now, what do you do instead? Well, we found that you basically increase the speed of these protocols, you get better collection of platelets. Typically on a fixed angle centrifuge, we'll typically recommend 1,000 RPM for about 5 minutes. It gives the chance that more of the cells will actually go to that upper layer, okay? Very, very important as well. Have a look at all the data, okay, that's been previously published on this topic, and I'll show kind of, more recent research that we've done on this topic as well. This is real life living cells, okay? This is the size of them. I want to make a point because look at the size of the platelet. It's pretty small, so it can easily, get by red blood cells, etc. But the white blood cell and the red blood cell are almost the exact same size. The white blood cell is a little bit lighter. So if centrifugation is carried out appropriately, you should be able to theoretically get them in the upper layer. But it's very, very close between the weight and the size of these two cells. So they're much, much harder to concentrate. And it's the reason why, whether or not you do the LPRF protocol or the APRF protocol, you don't see a big accumulation of these cells in those upper layers, okay? When you actually spin, always remember that the cells are separating based on their density, okay, between the RCF min and the RCF max here. And so whatever the difference between the max and the min, whatever that difference is in the G-force, that's how effective your layer separation will occur, okay? And of course, if you want to maximize this, and this is what every medical lab will do, is you grab a horizontal centrifuge, right? Why do we do this? Well, it's very simple. If the tube goes completely 90 degrees now, it allows the biggest separation difference between the RCF min and max. And always remember that the further away you go from this rotor, the higher the G-force back there, which means that the more of those cells are going to get pulled down to the bottom. So the heavy cells actually go down to the bottom much faster. It's logical, right? In a lab, we only ever use horizontal centrifuges. Why did we ever use fixed angle centrifuges for platelet-rich fibrin? Several reasons. One, smaller devices. So they're smaller, they're cheaper, okay? They're cheaper as well, which means that you can easily get a little office centrifuge that was this big. Now, for those that did PRP, and they're familiar with the old harvest systems that Bob Marks and Arun Garg brought to market, big systems, expensive, $5,000, $6,000, $8,000, they were bigger. They were actually designed as their horizontal centrifuges, okay? Horizontal centrifuge has been around for 50 years. In fact, the godfathers of the whole platelet concentrate knew that if they wanted to separate layers appropriately, they go horizontal, okay? It's over time, we've kind of lost, reason why we're actually going fixed angle versus horizontal. So, we were proposed to start doing research on this topic, and we started doing it. And for those that have never seen this before, it's very simple. The tubes, they go in up and down, and then they swing out. So when this thing actually starts spinning, the tubes, they go horizontally, then you can have proper layer separation, okay? Not rocket science. Like I said, I'm not an inventor of this or anything of that kind. And that was the whole concept behind BioPureF and why we actually started working in this field. Now, again, bigger separation of the G-force, which means that I got an easier time to separate these layers. That's advantage number one. This was a big one as well. Have you ever seen this after spinning on a fixed angle centrifuge? The answer for people that have done enough PRF, they say, of course, every time that I finish spinning, it's on an angle, the layer separations, right? And worse than that is the following. When you have a fixed angle centrifuge, when you start spinning, all the cells, they go path against the back, okay? First thing that happens, all the cells go to the back, and then they separate up or down based on their density, okay? The problem that you have is, this is exactly what you see when you look under a microscope. You see all the cells in the back, you see all the red blood cells back there, and you see these little platelets, and they're getting trapped by these bigger red blood cells. And if you think about it just logically, if you're on an angle like this, and you're a big red blood cell starting up here, first thing that happens, you go boom, and then you start going down along the back. If you're a little platelet and you start down here, you still go boom, you're lighter, you gotta start climbing up. You're climbing up this mountain on a fixed angle when all of these big red blood cells are coming down, trapping you and preventing you from going up. And that's the problem with using fixed angle centrifuges. When you go horizontally, and as can be seen in this picture, it's very straightforward, right? It's very logical. In fact, it's very easy to understand that these cells, they just separate through relatively easily, okay? Have you ever seen this? All these little dots here. This is another thing that people report as well. What is this? This is very easy. Conceptualize this. When you see something like this after spinning, those are all the red blood cells that literally smashed against the back there. And when you look under a microscope again, you see all these little clusters of red blood cells all the way down, not just at the top where you can see it. They also exist down here. And then you see a lot of platelets down here that were trying to make their way up, and they get stuck under these clumps, okay? And again, that's one of the reasons why in a lab, you would never ever use a fixed angled centrifuge, okay? They're typically cheaper devices, and they have different roles. Now, good paper done by a Japanese colleague. He looked at the way that we were separating the layers, layer by layer in the liquid. He said, I'm gonna do the same thing with a platelet-rich fibrin clot. I take a membrane, I'm gonna chop it up in different pieces, and then I'm gonna look histologically at what's going on. In his paper, he called it from the rotor, distal surface, okay? And that's kind of a cool name, proximal surface, distal surface, right? Kind of reminds me of teeth and the work that we do in dentistry. But in anyways, he found in brown here, sustaining for the cells, all the cells, again, in the APRF groups were located on the distal surface. Now, it's not just the APRF or the, one group, it's all fixed angled centrifuges. All the cells will always accumulate, again, on that back surface. This right here is something that I reprinted in one of my papers more recently. I find this table insanely interesting for the simple reason that it gives the density and frequency of these cells. We forget as clinicians, because we're doing big jobs, all these little details and how important they are. Look at the density of platelets versus white blood cells versus red blood cells. You can see some of these white blood cells are almost the same density as these red blood cells, okay? So that's one thing, they're very close. And I showed you guys sizes, you can see they're very similar. More importantly, look at the frequency. 5,000 white blood cells per microliter, 5 million red blood cells. You forget that. I'm sure you forget that. But the reality is that if you're actually trying to optimize platelet-rich fibrin and you got that fixed angled centrifuge, every time that you have a white blood cell trying to go up, think of how many more red blood cells you got going down. There's 1,000 times more red blood cells, okay, 5 million versus 5,000. There's 1,000 times more red blood cell. Every time one white blood cell is trying to make his way up, there's 1,000 big red blood cells going down. And that little one white blood cell somehow has to try and make his way through to the upper layer, okay? Good luck, right? That's the end of that story. Good luck. And again, that was, we published a paper on this, and it's a big one. Like I said, a very, very good study that's coming out in 2020. Not out yet. It was actually the evaluation of 24 protocols. I just got it accepted about a week ago, still not online. What we did is we got funding and we said, in this field and in this space, there's never been a research group that actually characterized exactly what's going on after the protocols. It's like, I can ask you, Omid, and I say, well, why are you spinning at 1,300 RPM for 8 minutes? And you say, well, somebody else told me to, right? But the reality is there's never really been a good optimization of these protocols. And it's very expensive to do this research, actually. This project probably cost us over 100,000 US to do it. And thankfully we got a research grant for it. But what we want to do is we said, okay, let's spin at 100G for 3 minutes, 5 minutes, 8 minutes, 12 minutes. Do the same thing at 200G, 400G, 700G, 1000G, and 1200G. 24 protocols, 240 mLs of blood, all from the same person. And we're going to run this on multiple people. We're going to see exactly how these cells separate at different protocols. And I can show you, I can say, look, Omid, take a look at this one here, 100G for 12 minutes, and this one 1000G for 3 minutes. They look exactly the same. To you, they look identical. All you see is this much normal separation. I can tell you to grab IPRF from either one of those and it looks identical. But the truth is, inside there's completely different layer separations that's occurring, okay? And it's one of the reasons why, this research paper in particular has been very useful in the field. Like I said, for those that want to learn more, like I said, have a look at the BioPRF website. There's a lot of data, and we're starting to put a lot of these papers, available online for free, just so people can learn more. And I'm only doing it to try and improve, healthcare. Very straightforward. You can go on Google. This is all just from the internet. You can go on Google and do a search, fixed angle versus horizontal centrifugation, and all of these different websites will come up, okay? Go online and do the search yourself, see what it says. Online, you'll read, they'll talk about swing out buckets and what they do. This rotor is particularly useful when samples are to be resolved in density gradient. The longer path, okay, length permits better separation of individual particles types from a mixture. However, this rotor is relatively inefficient for pelleting. When we take platelet-rich fibrin, we are separating as well based on density. So it makes perfect sense to use a fixed angle horizontal centrifuge. If you ask any company, if you ever called a company and you say, this is the job that I'm trying to do, I'm trying to separate my cells based on their density, which kind of device should I use? Every single centrifugation company will say horizontal, absolutely. What is fixed angle centrifuge used for? It's for pelleting. What is pelleting? It means that you accumulate cells at the bottom. And there's a reason why fixed angle centrifuges are better for that. The reason is pelleting means, and we do this in stem cells, sometimes in a liquid, I got a lot of different cells and I want to pellet them down to the bottom, which means I want them all at the bottom. That way I can remove the upper liquid and just keep the remaining cells there. That's called pelleting. If I do it on a horizontal centrifuge, if I have a cell here and I want to accumulate all my cells at the bottom, on a horizontal, I got to wait for that cell to go all the way down to the bottom. It takes a long time. If I have a fixed angle, it's much more effective. The cell that's here just goes boom. When he goes there, he just slides all the way down to the bottom, and then you pellet. Okay, that's pelleting. And when you do pelleting in a lab, this is what it looks like. These are cells that have been pelleted at the bottom. This is what, okay, you do with respect to cells pelleting. And that's, again, the angle, you can see it on a fixed angle. And this is what you typically use a fixed angle centrifuge for. This is not what you're trying to do with platelet-rich fibrin, and reason why we don't typically use these, okay? And again, it's typically why you see this on a fixed angle centrifuge, or the angles there is a result of all these cells that are accumulating on the back, okay? Another thing that we learned that was cool, I didn't know this at the time, I learned it from a website just doing searches online. Larger radius, higher RCF, shorter spin time. Tube centrifuge and a horizontal centrifuge experience a larger radius, resulting in a higher RCF and more efficient forces. Higher G forces produce a better seal with the tube wall due to packing. Okay, the time required for complete centrifugation is only 2/3 of the time required in a fixed angle centrifuge. I said, that's interesting, 2/3 the time. Okay, and on the website, like I said, I'm putting these here just so you guys can go online and read it. 15 minutes this way, 10 minutes this way. I said, ever cool. I said, think about what we're trying to do with platelet-rich fibrin. You are trying to separate these layers before it clots, right? So if you have a centrifugation device that can literally take 2/3 the amount of time and not bang the cells against the walls, because now I got a bigger radius, so the G-force separation is better, a protocol that would last 12 minutes on a fixed angle is only going to last 8 minutes on a horizontal, which means that I can more quickly separate my layers. An 8-minute protocol, I can get it done in about 5 minutes, okay? Because it takes 2/3 the amount of time. So that was quite interesting to read that as well. On the Eppendorf website, like I said, gradient centrifugation definitely requires a swing up bucket. You read these directly on their websites, okay? Very, very cool stuff here. Now, tubes, I'm gonna spend just a few minutes on this and then we'll be done. We did some quite interesting work, oh, I'm gonna go back here, quite interesting work here on this topic. And what we were doing at the time was we were trying to figure out how much vacuum you can get in the tube and how fast you can fill these tubes up, okay? And sure enough, when we were actually filling these tubes up with water, we started to see some of them actually had chemicals inside of them, okay? And this is a simple test that I recommend people do. When you fill up these tubes, they should have no chemical additives inside of them. Some tubes, okay, you can grab different companies of different types of tubes, and I don't care which companies you use, but have a look at this, okay? This, you take this red top tube, all of a sudden it's foaming up, okay? All these chemical additives inside. Okay, so I always tell people, you know, be careful with the tubes that you use, make sure they're actually devoid. These are the ones that we use in our research papers. These are the APRF tubes from 2017 or 2018. When we were doing the studies back then, you fill these purely glass tubes up with water. These ones here don't have any chemicals inside, okay, plain glass tube. Be real careful with this stuff because even from the same company, different batches will have chemicals sometimes, no chemicals. It's not very well regulated. So you have to make sure that you get a decent batch. Some of the more modern ones, even from the same company, like I said, will actually have, you know, you fill them up, they got all these chemicals inside, okay? Be very, very careful. A lot of people have complained about this, and I've had a lot of people write me pretty bad emails regarding the tubes because, again, we were promoting some of these, their uses, and again, be very, very careful. Now, the person that has really hammered home on this topic, his name's, group's named Quasi, Evidence for Contamination of Silica Microparticles in Advanced PRF Preparations. What he did in his study, he took a tube, he spun, he made PRF clots. He took the clot out, he put it in a Petri dish. He then enzymatically digested everything, all the fibrin, everything's gone, and only what was left over, he then took SEM, and that was the microparticles that were left over. And this is what he was finding, okay? And amazingly, the most amazing thing is, even from the same company, not every single batch will be the same. Some batches will be okay. The next batch has some chemical additives inside, okay? Again, no explanation for it, but be aware of it because it caused a lot of issues and a lot of failures occurred as a result of it. In the process of doing this, I started doing a lot of research on tubes, right? I'm a researcher, so we're trying to figure out what's working better, and we're trying to relay the info to companies to make sure that they're making better decisions. So I got a whole bunch of tubes. I started realizing that the more hydrophilic the tube was, the better the clot was. And so I would work with chemical engineers and I said, design me something that's going to be very optimized here, okay? When we did this, I want to show you a little video here. And what I did was I took different tube types. So I took 2 of the APRF tubes, I took 2 of the Intraspin and 2 of the glass tubes that we had developed that are very hydrophilic. Okay, I had my blood drawn here. And we drew them up in a random order, so 6 tubes, okay? And then it's spinning here. I'm just showing a little water test. After the 8-minute spin cycle, I'm gonna show you the results here, okay? Big differences here. So here, the tubes are coming out, okay? These are very hydrophilic tubes because we understand the biology. After the spin cycle in all of these tubes, 8 minutes, every single time you can take that tube and flip it upside down. The whole thing is clotted. Why does it clot like that? Because it's very hydrophilic, okay? No chemicals inside there. It's simply good science. Not more expensive to buy them, just better science, okay? That's my own blood, like I said, that was just drawn. Okay, you can literally take it, flip it upside down. And like I said, I posted this on social media here in North America just to make people more aware of it. When you take another tube, look at this. This is the Intraspin tube. Look at it, still liquidy. Same person's blood, same protocol, everything's the same. Okay, everything's the same. It's a tiny membrane, okay, not clotted. Why did that happen? Only because of the difference in the surface properties of these tubes. And that's why I always say that's the other one that I drew, the glass one. Okay, completely upside down. I can literally take it upside down. And amazingly, after I posted that, of course, I was sharing this knowledge. People started using these tubes. All these people on social media started posting, photos of themselves with the tubes upside down. And just by looking at this, look, I can look at this guy right here. Was it spun on a fixed angle or horizontal? I can tell right away. Fixed angle, horizontal, right? Now I can start figuring out just by looking at these, what people are spinning on. And it really made a huge deal. Like I said, a lot of people started commenting on this. This right here is one thing in PureF technology that I think needs to be improved across the entire world. Everybody needs better tubes. I'm not saying that we have a final solution yet. I still think we need to do more research on it collectively, all companies, etc. But it's one area that I think requires a lot of research today because the idea of having chemicals in tubes is obviously very bad. The idea of not knowing when the chemicals are there and when they're not there is terrible. And the tubes are not expensive. So we need to find a way to get these cheaper and into the hand of more clinicians to benefit patients. We've done the research, of course. How much bigger are these membranes? They're about 200% bigger and they're stronger as well. Okay, so I'm not going to go over all the data here. If you want to read any of these papers, you can go ahead and read them. Dr. Kawazi out in Japan, again, he's just been hammering on this concept, showing people that cells are dying because of the chemicals, etc. All this is published now, so it's available. And I highly recommend people read this stuff because, like I said, for those that are using PureF a lot, figure this out. My recommendation, when you're not sure, because some people are going to be listening from Iran or Europe or Asia, wherever, it doesn't matter where you live, simply do a little water test and you can figure out very, very quickly, kind of what's inside the tube. Now, last thing, this is only going to take 2 minutes, so I'm going a little bit over my time. Probably the biggest breakthrough in research that we've done more recently is respect to heating platelet-rich fibrin. Why did we do this? Well, we can extend the PureF membrane from 2 to 3 weeks, which it typically lasts 2 to 3 weeks, to make it last 4 to 6 months. Okay, that work's done, work's published, big animal studies, huge differences. Means that you want to use PureF as a barrier membrane, you can't do it because it only lasts 2 to 3 weeks. If you adapt this kind of technology and this technique, then it works effectively, okay? And I'll show you work that we've done over the past year. Did a lot of work. There's been a lot of groups that have done work with this little heating device, including Dr. Murao from Brazil and his group. Dr. Gano has done some work in Italy. And I think Silferdent's got a similar device. But long story short, what we're doing here is you separate layers based on their density. You take the upper platelet pore plasma layer and you put it in a heater. By heating it, it changes the properties of albumin. So they basically reorganize themselves in a three-dimensional shape. And it looks like this as opposed to liquid. It looks like an egg when you cook an egg that goes from clear and then turns white. It's the same process. And what happens when you do that is that it actually lasts a lot longer. And so the animal research that's been done here, this work we just submitted it for publication in Platelets, and very, very cool. This is an animal that's been on one side, a membrane was placed, on the other side here injected with Alpuref, what it's called. And this is representative several months later. That little Alpuref is still there. Okay, amazing. That little bump there. And if you think about, if you want to do a filler, let's say a girl comes in and wants, bigger lips. I don't need to use a chemical anymore. I can do that totally naturally with this technique. And that's where it's being heavily utilized. Like I said, you look at this stuff, fully biocompatible. Of course, it's coming from your own body, integrates well, vascularization occurs, and it just sits there and lasts months, which means that for us that work in the dental field, and this is just a protocol, we drop the liquid, we put it in the heater. 10 minutes later after heating, it looks like this versus like this. We use one of these female Luer lock syringes, and basically you just mix it together. So I got a little video here. This is how it mixes, okay? Super cool. All you do is you pass it back and forth. And this, we do very similar things in facial aesthetics where you can mix a filler with it, or for example, the work that we're doing in perio right now, the pockets, we can mix it like this with antibiotics. You take a little bit of antibiotic, a little bit of liquid Puref, away you go into pockets. So a lot of possibilities that now exist with this new technology. And a little video I made in August last year in Bern, Switzerland, when we started working with this. Look at the consistency. So it looks very different from what you're used to. It's a lot thicker. And at the time, we were actually creating these membranes. So we were creating membranes and we were placing this over top of titanium meshes in oral surgery department. Why were we doing that? Well, because titanium meshes have a higher rate of exposure. We knew that this was going to last 4 to 6 months. We knew as well we could make it as thick as we wanted to, which was cool. We could make it thin, we can squash it down. We're investigating it. So all these things are completely new. And then using it over top of titanium, which was quite cool. We were just making it. Within a few seconds, it becomes basically membrane. So it becomes sticky and you just peel it off and put it over top of something and use it as a barrier. Totally natural. Okay, only costs a few dollars. After that, we made these little trays. Okay, we call these little bioheat trays. And these are specific shapes. So you want to make a 30 by 40 collagen membrane. Here you go right there. You want to do a tunneling procedure for grafting and perio. There you go right there. You got a nice long one. Extraction sockets. People were using these ones here for diabetic, wounds, etc. And, started playing around with all these things. If anybody wants a copy of this paper, like I said, you can send me an email and I'm more than happy to share it with you guys. Look at this in the facial field. Okay, look at this lady. Look at the marionette lines here, the nasolabial folds, all the wrinkles here. This person was treated 100% naturally. Amazing, with these fillers that last several months, okay? This was done in combination with lasers, so we use the photon laser and as well as some injections, but amazingly, this is 100% natural. And when you're a clinician, you have these things in your office, this didn't cost me anything to do, apart from my time and a few bucks for a couple syringes and a couple of tubes for $1 each. This cost me virtually nothing. If you try to do this with fillers in the facial field, this would cost you hundreds of dollars in the fillers, okay? So very, very interesting. And like I said, at the end of the day, much healthier for your patients. This was one that I think is very cool. I did this work here with Dr. Scott Dabaccio, one of my colleagues that I work with down in Naples. And this, what you see here, is the membrane that lasts 4 to 6 months on the outside and the sticky bone on the inside. And what this is now is something that we can take a ridge and you want to do a horizontal augmentation. All I do is you take this thing, boom, lay it on bone, okay, the sticky bone's there, and the outer is already a membrane that's made. The way that we do this is we take that little bioheat tray. First thing we do is we make the Alpuref membrane, so the membrane that lasts longer, okay, we squirt it in there. We wait for it to set. We sprinkle on a little bit of allograft in there, or bone particles, put in a little bit of the standard liquid platelet-rich fibrin or IPRF, wait for it to clot the sticky bone, and then we take that out. On the back end, we got the membrane that's slow resorbing, 4 to 6 months. In here, we got our standard sticky bone. Take it and boom, away you go, okay? A lot of possibilities, like I said. And I think with this stuff here, like I said, the future.
Hello, my name is
very
Dr.
bright.
Rick Miron, and I'm very happy to announce our new online PureF course. Because many people have been coming to the courses and wanted an online platform, I'm very happy to offer this new convenient way to learn. It's going to be a 9-module program for 8 CE credits, and it'll cover biology of wound healing first in module 1. We'll cover differences between PRP and all the advancements to BioPureF. In the later stages, we'll go over phlebotomy techniques. We'll go over the clinical indications of PureF. There'll be a nice section on facial aesthetic use for PureF. And then we'll wrap it up with kind of the new research that we've been doing on the AL-PureF and C-PureF protocols with a live demo. And so I'm very excited to announce this new program. It's available at www.plets-rich.com. And I look forward to future feedback from colleagues. Thank you.
Actually forgot that I put this in here when I was preparing the slides. I've already done it. So it's an online platform and a program. And I did this some time ago, because I was teaching so much PureF courses. And I was not expecting, obviously, coronavirus to come and all these things happen. And I use it just as an easy way to educate doctors that want to learn platelet-rich fibrin. Over this coronavirus thing, a lot of people have been registering for it and learning about it. I created a special coupon code for all of your colleagues, and the code is 50% Omid. So I just named it after you. It'll give people half off the program. Okay. Like I said, I'm only trying to educate people and trying to advance that field. So for those that actually want to learn a lot about platelet-rich fibrin, how to use it in dentistry, this is just a small little section on platelet-rich fibrin, kind of an overview of the later research. But if you want to see how we use it in perio and how we do sinus grafting and GBR and everything else with it, like I said, that's a very good program, and I'm happy to give discounts for all of your colleagues that way there. And if anybody has any questions, like I said, this is my email address, so it's rick@themyronlab.com. Anytime, like I said, I'm happy to answer any questions thereafter, and I'm also happy to answer questions that you're going to have for me as well. Thank you
so much. Thank you so much, Rick. Full of information. I think myself, I have to listen to it 2 to 3 times more to get all the points, because it was very rich in information, and I really appreciate all you've done in this field. And truly, you are one of the references that everyone in the world, if they have any question, really can easily go to your articles, to your educational courses, and I really thank you for that. And as he mentioned, all the audiences, there is a very, very benefit and good point he mentioned, the coupon 50% Omid. You can go to his website and you can get to these amazing courses with the 9 modules you mentioned, right?
Yeah, it's 9 modules, and they're well done. You get C credits for it as well, but the way we did it was that every single module would cover a different topic. So one would be, just basic science, like I showed here. Another whole module would be just on tubes, everything you need to know about tubes. Another one, just how to use it in dentistry. Another one was just facial aesthetics. So it's really good because it covers everything A to Z on the topic.
And especially, it's a good chance during these days, so people can just be focused on this education.
Yeah.
There are lots of questions, but I just picked 2 to 3 or 3 or 4 questions. Actually, you mentioned them all, but I just want to have a review over it. First of all, about the tubes. We have plastic ones and we have those made of glass.
Yeah.
So if I remember right, you mentioned that those, if we want to have more liquid and more hydrophobic and not hydrophilic, we should go with the plastic ones, right?
Yeah.
And all the companies with all the machines, do they have all the options, or, for example,
I don't think so. To be honest with you, they all vary a little bit. So for example, BD sells pretty decent glass tubes, but they don't have any plastic alternatives. Those ones there have anticoagulants, and so you really gotta be careful. And some companies have good of one type and not good of the other type, and so sometimes you got a great one, and then all of a sudden chemicals appear in future orders. I mean, it's just that whole field. Like I said, the problem is nobody's really designing a PureF tube, right? When you look at the companies, what the companies do is they go find a tube that kind of suits and does the job. And then they say, okay, even if it's a dental company, they'll start buying and reselling those tubes for PureF.
Yeah.
But the tube itself is not made for PureF. It's made for some other job. It just so happens to suit what we want intended for it, right?
Yeah.
And so that's typically what happens. And so a lot of people around the world are in the search. Like I got a lot of colleagues from India and they're like, what tube should I use? Well, you know, the tube options there are not the same that we have in North America. They can't just go get, you know, a vacuette tube that we would use, a white one. They got to go find something else. So it's the reason why I don't try and tell people use this tube or that tube. I try and say, understand what you're doing with the tubes. Then when you understand, go to the company and say, this is what I need. I need a very hydrophobic plastic tube. What do you have? Test it, make sure there's no chemicals inside. And then from there, you know, you can get a good outcome.
And in one of your studies that I was really interested in, you mentioned that those groups that they used process tubes with intra-spin machine, they had the most amount of platelets available.
Yeah.
So just again, as you mentioned, I just have this question. Is there any way to recommend a good machine to those who want to use PRF? Because there are so many varieties, different machines, different tubes. So for example, if someone decides to buy a machine, regarding all the machines available nowadays, what's your recommendation? Because different RPMs, different, you know, everything is different, different protocols. And as you mentioned, for example, an intra-spin machine, 2,700 RPM for 12 minutes. It's very fast. And as you mentioned, we can have more platelets with less speed.
Yep.
And so I just want to have your opinion and your suggestion, recommendation actually, to those who want to start working with PRF machines.
Yeah. So of course, naturally go for horizontal as opposed to fixed angle, right? That's the first step. If you don't have one, just go horizontal. And then we purposely, in all of our studies, we report G-forces on purpose. In our studies, we no longer use RPMs because G-force stays consistent. Whether I got a machine that's this big, this big, this big, as long as I spin and the protocols that we've established, they're all for any system now. And we did that on purpose in our research group because I didn't want to fall into this trap of saying only use this machine or that machine or this machine. So that's number one. Number two, of course, there's going to be small differences between qualities of centrifugation systems. So when you see one machine perform better, for example, intraspin, an intraspin machine is pretty well built as a fixed angle, and you'll get a little bit better results as a result of that. Sorry, I got the guys in the back cutting the grass back there. But anyways, on a horizontal, there's different qualities. Does it make a huge difference? Not so huge. Okay, so I would say just go and get a horizontal one and then get the protocols from our papers for liquid, for solid PureF, and use those ones there. The best machine that I know of that we use in our research papers is Eppendorf. It's a German brand. It's an Eppendorf 5702, and that's the machine that we've done majority of our research with. If you go to any research lab, they're all going to recognize the name Eppendorf. It's the biggest company in the world for selling centrifuges. They're a $1 billion a year company. They sell many of them. The problem is that those machines are about $4,000 each just for the centrifuge, okay? That's not a company price. That's just the actual price of the device. It's a very good system. Then you can go a little bit cheaper, of course, or, you know, better. I mean, it just depends on what you want to spend and what kind of quality you want to reach. You know, it's the same thing as driving a car or anything else. So again, the main message here is choose a horizontal one, number one, okay? Use the right protocols that we've designed in our papers, which I would recommend, and use the right tubes, okay? It's very simple. Get the right tubes, get a horizontal machine. Then you'll be much better than any fixed angle centrifuge, for instance, or any tubes that have chemicals inside. So.
And one more thing regarding the last part of the presentation, to make long-lasting membranes, PRF membranes, that you mentioned that we should put it on a heater or something with the bioheat, the kit that you showed. Is it specific to a machine, or they can do it with all type of centrifuges?
You know, we have developed actually from the lab the bioheat device, and it's a heater, and it's specific. The way that it works, I wish I had a photo of it, but anyways, it's at the top, there's different little holes, and it's for different syringe sizes. So if you have a 3 ml syringe, it goes here, or if you have a 5 ml. And so you just place it in there. And the advantage and the reason why those things exist is that we get a tube that's skinny, and then the heat comes from all directions. And so, you know, if I just laid it down flat and applied heat one way or the other, it might not get the entire heat. So it's a very fast way to heat things, right? Those devices are not very expensive. You know, you'll save so much money on saving from buying membranes over the next years that you'll save a ton of money. And they're about...
Protocol for heating is available in your article, right? So there should be a protocol. Yeah.
Yeah, the protocol is fully described, both the centrifugation speed as well as the heating. It's 75 degrees Celsius that we heat for 10 minutes. But like I said, it's got to be a device that's able to transfer heat in all directions. Yeah, you know, to make sure that it's equal. Right? I wouldn't want to just take something and put it in a microwave, so to speak. You know what I mean? Yeah, so it's got to be properly done.
Exactly. And Rick, my final question: the 90 seconds importance that you mentioned for having the blood and putting in the device. What if a surgeon or the practitioner want to collect more than 6 tubes?
We have 2 machines, obviously. You know, if you go to any of the top...
So if I have only 1 machine, so I cannot do it?
It's not possible. Yeah, I wouldn't recommend doing it by any means. Yeah. If you're one of these guys that do these bigger procedures and you're doing more often, you know, bigger cases, the Mike Picos of this world, etc., then they all have 2 devices. They all understand the biology on what's going on, and then they'll just get 2 devices to spin 2 at the same time. Most things you're going to do in dentistry, you can get away with just having 6 tubes. I mean, most things, regular implant, extraction, I mean, 6 tubes, 6 membrane. And think about it. If you're actually using the right tubes, you're going to get a much bigger membrane. We've shown in our studies, right? My membranes are probably twice as big as the average person because you're using these tubes that there's still liquid in the top, and we don't have that. Like I said, we have it so that the whole upper layer is a nice big clot with many cells, and we just take out a big chunk. And so those membranes are bigger. 6 tubes is a lot.
Yeah.
And we can do a lot with it. But, you know, you can still do it. Like I said, just understand, I'm just teaching people, right? Understand that there's a lot less cells in there now, and it's the reason why that membrane is a little bit smaller. Yeah. So the next time you see that, or if you're in your office and you have your staff that's doing the blood draws and making the PureF, if you take a look at 8 membranes and you say, hey, why are these ones here, you know, 30% smaller, 40% smaller? In the back of your head, you know, hey, wait a minute. We must have an issue with the amount of time from start to finish that we're getting this into the system.
Rick, I don't know how to thank you enough. Really appreciate your time, your valuable knowledge to share with the world. And I'm so thankful that you accepted this invitation. We really enjoyed your presentation. And again, thank you so much for your timing. Hope to see you very soon, and hats off. Thank you so much.
All right. Thanks for having me again, and nice seeing you. Glad to see you're always smiling out there, and we'll keep in touch, and hopefully we'll be at a conference sometime soon, and everybody will be well and happy, and this COVID thing will be behind us. So thanks again for having me.
Thank you so much. Take care. Stay safe. Thumbs up. Thank you.